Hello and welcome back to another video come the OCI GCSE computing course. Today we're looking at topic number 13, and this is the last topic in this data representation chapter, and it's about how instructions are represented by a computer. Quite a heavy video potentially, so maybe make notes if that's appropriate. If you're not revising the night before, make notes perhaps, that might be useful because there's a lot of information to cover in this video. So let's first have a look at something. We're almost doing a pre-recap because I'll cover some of this stuff in a later video in quite a few topics time, but we have a spectrum for programming languages. At one end of the spectrum we have what's known as machine code, and machine code is essentially the binary numbers, so zeros and ones, just lots of bits patterns, and a computer can understand all of this, but someone looking at this who's not a programmer would just see zeros and ones. It would mean nothing. And machine code are the raw instructions used by the CPU in the form of bit patterns, and we'll look at bit patterns in a couple of minutes. So at the other end we have ordinary languages, so sometimes called natural languages. So unless these are English, German, etc. So unless it was taught to, a computer was taught to, in the case of artificial intelligence, which is really basic at the moment, but I'm sure in 50 years time will be a lot more advanced. A computer can't understand ordinary languages because in our head, in our brains, the words are represented by images. So if someone who's born deaf, for example, in their head they will think of words in the form of images, not words or sounds, if that makes sense, because they've never heard sounds. So computers can't understand this. Only humans with our complex brains can understand ordinary languages at this current moment. So yeah, for example of this, if you inspect them, English or German. Then you have programming languages such as Python, who consist of mainly words, but some numbers and some things that a non-programmer wouldn't understand. Then you have other languages such as JavaScript, which are further down, then C++, and then you have what are known as assembly languages, which are sort of what things are written in, which are basically machine code. And this is so essentially only machine code and assembly languages, they're regarded as low-level programming languages, and the rest are sort of high-level programming languages. They are closer to normal languages, normal with words. People that these programming languages non-programmers could in theory understand, maybe less so at this end. And then you have these low-level languages which only specialists could understand, maybe even none at all if it's just machine code. We'll look at this in more detail in a further video, but this is sort of like a bit of a recap, hopefully. So it's important to understand that a programming language, or just to make sure you appreciate that a programming language is simply used to communicate instructions to a computer. Use a programming languages to control a computer in some way. So let's have a look at what bits patterns are. I mentioned them just before. So bits patterns essentially are the code represented to represent instructions. So when you execute a computer program written in a high-level programming language, what is known as a translator converts the instructions into machine code. Again, translator we'll look at in more detail in a future video, but a translator translates what you've written in a programming language into the machine code so the computer can use it. And the machine code is in the form of patterns of bits, binary digits which are 1 and 0. For example, this is just showing an example of the processor, how it represents it. You do need to know all this. So here we've got a instruction in Python, 5 plus 10, very simple. The computer it doesn't understand what that means, because it just doesn't understand anything other than binary, so it has to convert it. So each high level instruction is split into smaller low level instructions in the form of machine code, and these low level instructions are split into what is known as an operator, which is essentially the instruction, and some may also call it a opcode. I've seen it written, the exam board use this, but they also allow operator, which is what I was taught, and an operand. And operand is essentially the data. I had to double check this stuff because it doesn't actually say in the spec, but this definitely, exam questions have come up on this, and they probably will come up again. So in our example here, 5 plus 10, the plus sign is an example of the operator. It's telling you what to do, it's the instruction. And the data involved is the 5 and the 10, and these are the operands. So the way it would do this, different processors do this differently. So for example, an Intel processor, an AMD processor would do this vastly differently probably, but the same principle. But what they do, each operator and each operand are represented and stored in a bit pattern. so just ones and zeros. So for example here, if I'm using a nibble to represent each operator and operand, which it wouldn't actually do because that doesn't give you enough combinations, this 0010, so 2 in binary, will maybe be represented as add. This may be 10, this may be 2, and this may be 5. So this would sort of form this instruction. And like I said, I've just made this up. This wouldn't actually be used most likely. I don't know. I don't work for a processor company. I just know the theory behind it. And then we've got other ones. But as you can see here, hopefully you spot that this operator, this opcode here, is the same as this one. And that means that this, because we know it's represented by 2, add 10 to 5, this will also represent 2 as an instruction because it's part of an instruction set. So an instruction set, basically it's like a table with each instruction given a unique operator, which is basically what that says there. So if we have our code here again, I've done it by colours just so you can see it wouldn't be like this. This turquoise colour represents the operators, and each one will be part of a huge table that the processor is built with, that has a unique operator for each instruction. So this is add, this would be 2, and then we have the 2 repeated several times. So it can be repeated in a bit pattern, but each operator has a unique binary representation. So this being 2, this cannot be anything different because it's represented by the same binary number. So it's important to establish that each one is unique, and so that's how it understands what to do. So it's important that a processor can distinguish between data and instructions. So if we look at our bit pattern again, hopefully again you'll notice that here we've got our operand, and this is our operator or opcode, and it's the same. And I said that this has to be unique, the operator has to be unique, but the operand doesn't have to be unique. They can be represented by the same bit combination. And so the processor, for it to do anything with this information, it must be able to understand what is a bit, what is an operator and what is an operand. It must understand the difference. So the way it does this, it can't actually look at them and go, oh, this is an operand, this is data, this is an instruction. It can't just do that. It knows the position of it. So it knows, so in our example, and again I don't know if it's actually like this, there's no evidence to suggest that it isn't, because presumably this is very top secret information, because the competitors in the processor market don't want people to know how they actually work. To an extent, obviously the simple basics are available to know. So the way in our example, what it would know, it'd be programmed, the processor, when it's made, it'll know that the first 4 bits, the first nibble, is the operand, the operator, and maybe it'll know that the second 4 bits are the operand, and it'll know this cycle repeats. So it'll know that this is the 17th bit. It'll know that the next 4 will be the operand operator. It's difficult to get confused between the two. And just let me re-emphasize: the data is the operand, and the instructions are the operator. And it'll know, basically it distinguishes between the two by knowing the position of each. It'll know the cycle, it'll know the pattern, and that is important to know. So that's it. Next up we're looking at databases. Hopefully this video was somewhat easy to understand. It takes a while to get used to. Like I said at the beginning, if you have time, maybe make some notes, that would be useful. Go over the bits, rewind, go over bits that maybe aren't clear. Hopefully I've been as clear as possible. So yeah, thanks a lot for watching.